afternoon, everybody. I am Malus Ulong. This is my project for Mr. Roden's applied physics class in the spring of 2017. My topic is using physics to hit a home run. So basically the intent is to determine the optimal swing angle and swing speed that that you could use to hit a home run. This is mainly hopefully I can get my two boys to hit better based off using science to see if they can improve their hits when they play baseball. All right, so first off, the dimensions of a Little League baseball field is, you can see it right here. The minimum distance from home plate to any part of the outfield, the minimum distance has to be 61 meters. So it can't be any less than that. There's some fields that are further than that, but at a very minimum, it's 61 meters from home plate all the way out to any point in the outfield. All right, so that's the goal when you play baseball, is to hit it as hard as you can. If you hit it over the fence, you get a home run. You can score points easily, or runs easily. And if you don't hit it over, the further you hit it out, the harder it is for the people playing on the field to get you out or to get your teammates out. Okay, here is the side view of the field. We have this is a ball right here on a tee, and this is the fence. So it's 61 meters from where the ball is to the fence. That's what we want. That's our goal. That's what we want to reach. Is for eventually my boys to be able to hit it that far. All right. As you can tell, the level of the ball is pretty much at the level of the fence. It's about 3 feet up. So that takes away that factor. I don't have to factor that part in. It'll just go from here to here. This is the the horizontal line. Now, as we learned in our class, 45 degrees is the optimal angle for you to get the furthest distance on a projectile. Okay, and what we have here is I put the 30 meters per second is what the speed, the velocity of the baseball as it comes off the tee when it's hit by the bat. And we'll use those numbers to try to figure out what's or to try to solve the issue with my kids trying to hit the ball. Okay, so the first part is a swing angle. Okay, so like I said earlier, 45 degrees is the optimal angle to get the furthest distance on a projectile. But I'll show you right here. The baseball is round and the bat is also round. This creates kind of an issue. You can't hit it at a 45-degree angle and expect it to go as far as you want. Because as you can see, when you hit the ball, if you hit it straight on at an angle going straight, it will probably go forward. But because both of these, because the bat and the ball is round or circular in shape, the ball will have a tendency to roll off the bat. So it'll either go at an angle this way or an angle this way, depending on where you hit it. So actually hitting it at 45 degrees is not the best angle to hit it at. You want the ball to project out at 45, but the best angle, this best swing angle, is anywhere from 20 to 30 degrees prior to making contact with the ball. Also, the trajectory of the bat as it goes through this plane right here, you can see at the bottom, in order to hit it at a 45-degree angle, the batter must bring the bat all the way down and bringing it up. This If anyone's ever played baseball, this is kind of difficult to try to hit the ball at an upward angle. You're basically trying to hit it like a golf ball, and it doesn't work. You lose your power. As you can tell, the acceleration as it comes through through the horizontal plane, it'll take longer to get up to hit the bat. So you either have to swing a lot faster or you have a lighter bat. But the optimal level swing with the body mechanics is to go through this plane right here and come up right prior to hitting the ball at a 20 to 30 degree angle. That would essentially project it out at a 45 degree angle. All right. Okay, so we're going to do some kinematics. I have my information up here. Have an equation. It's I put position, velocity, acceleration, and time. All right, the position starts at 0. X is going to be 61 meters. Y, as I was going through this, I wasn't really concerned about the Y. So velocity for X naught, we have it. We'll do the equation. I'll punch in that number, and the velocity of X will be 0. Y naught, velocity of Y naught is unknown. Velocity of Y would be 0. Acceleration is 0, and acceleration for Y is negative 9.8. And the time is unknown. Okay, the first step we're going to do, we're going to get the velocity for X and also Y right here. So we have the diagram right here. We have 45 degree, and then the velocity of 30 meters per second. We go 30 cosine 45, we get 21.2. So we'll go ahead and punch that in up here. 21.2. Oops. And then 30 sine 45 for the Y also gives us 21.2. All right, so we have that information there. Now I want to know the time. I want to know how long it's going to take for the ball to get out of the park. All right, so I'm going to use the time to get other parts of of trying to figure out the best way to hit the ball. Okay, so I decided to go with this equation. X equals X naught plus velocity, initial velocity times time, plus 1/2 acceleration times squared. Okay, so we do have the distance, which is 61. I'll pretend I didn't write that yet. Velocity or initial position is 0. The initial velocity for X is 21.2, and time, and then 1/2 AT squared. Acceleration is 0, so that brings out to 0. So I went ahead, just left that at 0, crossed those out, and we're left with 61 equals 21.2 T. Divide that on both sides, and we come up with 2.9 seconds is our time. All right, so now that we have that information, we're going to go to the bat swing. We want to see how fast we need for the bat swing. Okay, so Newton's second law. For every action, there's an equal and opposite reaction. I know there's a whole bunch of other physics equations that would actually deal with changing momentum and speed, transferring from the bat to the ball, but I'm just going to go ahead, keep it simple because I was trying to figure out, but it's taking too long. I'm just going to say that the speed of the bat is equal to 30 meters per second. All right, so Jace, make sure you pay attention to this because it's for you and Ty. All right, so second law, based off of that, we're going to say everything that happens, the speed and the acceleration of the bat is equal to the speed and acceleration of the ball as it goes through. Okay, so acceleration is velocity over time. Our velocity is 30 meters per second over time, which is 2.9 seconds. And that gives us with acceleration of the bat, swing for 10.9 13.3 meters per second. All right, so if you accelerate the bat before you hit that fast, and then you reach the speed of 30 meters per second, you'll be able to hit the ball. If you have the proper angle, you'll be able to hit the ball out. Okay, now there's, let's see where we're at. Okay, so then I also put here, this is good, we'll come back to this again, but you can see if you were to hit the ball a lot, or swing your bat a lot faster, say at 40 meters per second, that'll give you an acceleration of 13.8 meters per second squared. That means your bat is moving a lot faster. Okay, so keep that in mind, because in conclusion, in order to get an optimal swing, you have to have the best angle, which we determined to be between 20 and 30 degrees, and you also have to have the fastest bat speed. Okay, so I'll use a force equation to show that if you swing the bat faster, you don't need such a heavy bat, or if you get a heavier bat, you don't have to swing it as fast or accelerate it as fast. So we'll use the equation force equals mass times acceleration. Here, force is equal to 0.8 grams, which is the weight of the bat, multiplied by 10.3 meters per second squared, which was the first acceleration, the number of acceleration we got for the first equation. As you can see, the force acting on the ball is going to be 8.24 newtons. All right, so now the next equation, we're going to increase the bat size to 0.9 grams, same velocity, same acceleration, and that gives us 9.27 newtons. So there's more force behind the bat if you have a heavier bat. All right, and then finally we have the same weight of the bat, but this time we're going to accelerate it through the batting zone at 13.8 meters per second, as you can see there. That's why I had the faster bat speed up here for faster acceleration. The force here is 11.04 newtons. So basically, if you want to hit a home run, you're going to have to either get a heavier bat, but still maintain a bat speed, acceleration of the bat through the zone at least 10.3 meters per second square. Or if you swing it a lot faster, you can use a lighter bat. Okay. Did you guys get that?
What?
Were you guys paying attention, or are you going to keep striking out this season?
No, I never. Yeah. It was
All right.
I only struck out like 5 times. This guy struck out every time.
Okay, so hopefully that helps. I hope I was clear enough. Probably not, but that's all right.
I didn't get it.
And good luck to everyone in the future, and hopefully you can stick it out. Good luck on the test or exam next week, I guess. All right, thank you very much. Bye.